In this video, we're looking at data representation for A-level computer science. There are three number systems that you need to know: binary, decimal, and hexadecimal. Sometimes decimal is referred to as denary, but it's the same thing. Each one of these number systems has a base number. Binary is base 2 because there are two different digit values available, just 0 and 1. Denary or decimal called base 10 because there are 10, 0 through to 9. And hexadecimal 16 because there are 16 digits available, 0 through to F. And we'll look at how that works a bit more later. So computers store and process data in binary form, in the number system binary. These are zeros and ones. And why is that? And that's because computers are based on switches. Digital computers use transistors as switches to decide whether something is true or false, or has one value or another value. So the fact that it's a switch means that zeros and ones are the most appropriate number system. There have been computers based on other number systems or storing some of the data in other number systems, but it's so much easier to tell if something is just there or not there, on or off, i.e. 0 and 1, than it is to try and store intermediate levels that you'd require for other number systems. In a binary, we have a number of different prefixes. There's a word or part of word that goes in front to indicate what multiple of those things we're talking about. In this case, we're talking about bytes, and we put a prefix in front of the word byte. So kilobyte means 1024 bytes, and that's 2 to the 10. So why 1024 and not 1000? Well, because 1000 is not a power of 2. 1024 is a power of 2. So all the binary prefixes are powers of 2. A kibi is 2 to the 10, a mebi is 2 to the 20, and so on. So every time you go up from kibi to mebi to gibi to tebi and so on, then you're increasing the number of bytes by 1024 times. Compare that to the decimal prefix that we're more used to, the kilo, mega, giga, and tera. These are multiples of or powers of 10, and therefore don't quite fit the binary number system. But they're still used sometimes, especially in things like marketing, for things like hard disk drive space and speed, because they sound bigger. Okay? A 400 gigabyte hard drive, for example, if you were to actually say that in gigabytes instead of gigabytes, it would be closer to 465, which doesn't sound as good. So binary is a number system. We call it base 2. The digits are 0 and 1. The word bit itself it comes from the idea of a binary digit, or the words binary digit. You combine those and you get bit. So a bit can have a value of 0 or 1. It just means it's a binary digit. We have column values or place values, and these are all powers of 2. We typically write the lower value to the right hand end of the number. So that means the number 1 is at the right hand end, just like we do for decimal. Okay, so the first column we call the units column or the ones column, and then we move up as we go to the left of the number. So in denary we go from 1 to 10 to 100. We're going up by multiples of 10 each time. Of course, in binary, go up by multiples of 2 instead. So it's 1, 2, 4, 8, 16, and so on. So a 1 anywhere in a binary number just means that you need one of those place values as part of your number. So the binary number 1011 means I need 1 in the 8 column, no 4s. I need 1 from the 2 column and 1 for the units column, or the 1 column. And we add them up and we get 11. So it's exactly the same as the way denary works. We just take the where there is a number value in the column, and add them all up until we get the overall number. So hexadecimal is base 16, and to get our 16 values we go from 0 to 9, which gives us the first 10. Then we needed to come up with some new way of having digit values beyond 9, so they decided to use letters. And we've got A for 10, B for 11, and so on, all the way up to F for 15, and F is the largest value you can have in a single hex digit, which is equivalent to denary 15. So here's an example: 10101111, and the first 4 bits of that, the first nibble, is A. We can see that is a value of 10, and 8 plus a 2 is 10. And the second one is, well, we can tell it's the largest value straight away because it's 1111. We can't get anything bigger than that, so that must be F, and that's 15. And if we break it down, 8 plus 4 plus 2 plus 1 is 15. So you need to be able to convert between these bases in any way. So let's have a look at how we do conversion. First of all, binary to decimal. Probably the easiest way of doing this is just write down the column values, as we did before, starting at the right hand end. The least significant bit is 1, column value or place value of 1, and then double it each time: 1, 2, 4, 8, 16, and so on. Just make sure you've got the right number of values, the right column. If you're asked to do an 8-bit number, then write down 8 of those column values and fill it in. So this number that we're giving here, binary number, is 10111. To work out what that means in decimal, we just take each place where there is a 1 and we add the value. So there's a 1 in the 16 column, there's a 1 in the 4 column, and a 2 and a 1. Add them all up and we get the result, which is 23. To go from decimal to binary is a little bit trickier. Here's an algorithm you can follow. So the first thing you do is find the biggest column value that isn't bigger than the number you want to convert. So for example, if we're given the number 30, then the column value of 32 is too big. So you want something that's exactly right or less than, but definitely not greater than. So the next available column down is 16. 32 is too big, 16 is fine. So what we do is, in stage 2, we put a 1 in that column. So put a 1 in the 16 column. And then we can subtract the column value from the original number. So in this case it was 30, we're using 16, so we take 16 away from 30 and we get 14. And then we keep doing that. I say we find the next column that's not too big, and then subtract that, and so on and so on, until we get down to a value of 0. And once we've got 0 left, then the 1s represent the whole number, and every other column that we haven't used can be filled with a 0. And again, just make sure that you've got enough columns. If you're asked for an 8-bit number, make sure you've taken into account all the numbers. Alright, binary to hexadecimal. So to convert binary to decimal, we split the binary into nibbles, i.e. blocks of 4 bits, and then you can convert each nibble independently. You can do one at a time. And then if you've got a value that's over 9, i.e. it's too big, then you start using the letters. So A, B, C, D, E, F, according to how big the number is you've got. So for example, if we had the binary value 11000101, we split that up into nibbles first of all. So we've got 1100 and 0101. We take each nibble in turn. So 1100 is 12, it's an 8 and 4, which is 12. And we check with this, write this down if you need to in exam, just to help you each time. So 9, 10, 11, 12, that would give us C. And then the rest of it, the other nibble, is 0101, which is 5, and we don't need to do anything with that. It's fine, it's within the range of normal values. It's a hex digit, we don't need to do anything to it. So the final answer, we combine those two parts together and we get C5. So C5 is the hex value of this binary number. You can do it for 3 things that are bigger than this, so 3 hex digits. If you had a bigger number than this, you would need 3 hex digits if it was more bits available. If we want to go hex to binary, and we're obviously doing this in reverse, we take, again, you can take each hex digit in turn. So I'm going to take the D, and D, if I scan along, that's 9, 10, 11, 12, 13, and rewrite that down as binary. So you can use the existing methods you have for getting the binary from denary. 6 we don't need to do anything with, it's fine, it's already a valid hex digit. We don't need to worry about it as becoming a denary number. And then we do put it into binary, and then we just combine the two nibbles together. So again, we get 1101 first part followed by 0110. Okay, let's at decimal to hexadecimal. To convert decimal to hex, there's a couple of ways you can do it. You can convert to binary first and then to hex, or divide the number by 16. So this way is pretty easy. You already know the method of doing binary to hex, so you can do it that way. The alternative is to divide by 16, and sometimes you might have to guess a little bit first of all to work out how many times 16 goes into your number. In this case, we've got 138 in denary. We want to find out how many times 16 goes into that number as a whole, and then find out the remainder as well. So in this case, 16 will go into 138 8 times and leave a remainder of 10. This is the first part of the answer, 8 lots of 16, and this is the second part, 10, which we would store as A in hexadecimal. So we put those together and we get 8A. In other words, 8 lots of 16 plus another 10 will give you 138. So this way is a little bit more taxing in terms of actually doing the division of maths. This way is kind of easier and a little bit safer perhaps. Right, if we're going the other way, hexadecimal to decimal, then we can do the reverse of that process. We take each hex digit and multiply it by the column value for hex, and then we add them all together. So in this case, say we had 2BF, we need 2 times the column value, which is in this case 256. It starts at 1, then 16, then 16 times 16, which is 256. So we've got 2 lots of 256. We've got B lots of 16, which is 11 lots of 16, and we've got F lots of 1, so it's 15 times 1. Add all those together and we get 703. So 2BF is 703 in decimal. Alright, let's look at binary arithmetic, starting off with addition. Addition is pretty simple. 0 plus 0 is 0, obviously. 0 plus 1 is 1. Now, 1 plus 1, you can't fit the answer to that within a single bit, a single binary digit. Obviously in decimal, 1 plus 1 is 2. You can fit it into a single digit, but with binary we can't. So what we do is we're going to carry 1. We can only ever carry 1 in binary because that's the biggest thing we've got. But when we're carrying 1, we're effectively carrying over the value of 2. So in this case we get 1, 0. That means 2 and a 0. So in total 2. 1 plus 1 is 2. Subtraction, very similar. We could do column subtraction in binary. Just write down your 2 binary numbers, one under the other. And this time, instead of the carries, we're going to be borrowing. So the same as for decimal, when you borrow then we can borrow for binary. Only difference is when we're borrowing from a column, there can only ever be one there, and so we're always going to be borrowing all of it, and that one actually represents 2 when we borrow it. So when it comes from the left column over to the right, we're actually bringing it over effectively 2. We'd still write it down as a 1 in binary, but we'll have effectively 1 0 we're borrowing. So that means we can always cope with numbers if we can borrow from the left. Now, you don't actually have to do subtraction inside the CPUs. We can use addition circuits that are already there for addition. All we have to do is we have to convert the number first, and we'll look at how we're converting numbers later on so that we get a negative version of a number. So for example, if you have to do 10 minus 5, you can actually do 10 plus minus 5. Gives you the same answer. But so we're using an addition circuit to effectively do a subtraction. Overflow is when the resulting number that you get from a process like an addition is too large for the fixed number of bits that you have available. So if you only have 8 bits available and you try and add 2 numbers together that make it bigger than you can store in 8 bits, then you get overflow. You can think of it like a bath and you're filling it with water, and if you put too much water in to the fixed size of bath, it can't expand, it can't change shape, then the water will just overflow. One way we can store decimal numbers in binary, another way of looking at this, is with binary coded decimal. In this case, each individual digit in the decimal number is converted and stored as binary. So for example, 93, the decimal number 93, we take the 9 and store that as 4 bits, and we take the 3 and store that as 4 bits. Now of course, that does introduce a little bit of wastage in that we only ever have to store up to 9, and we know from our hex work that we could store up to 15 in 4 bits. So it's a little bit wasteful, but there's a very good reason for using this. This avoids rounding errors. So when we've got applications that are sensitive, when we've got decimal numbers that we need to store very accurately without rounding, we can use binary coded decimal. It does introduce another disadvantage, and that's that calculations are more complicated to carry out. We can't just add these numbers together. So 2 binary coded decimal numbers represented like that in binary, you can't just do column addition and add them together. So you do need special process to actually do the additions then. We would use binary coded decimal in calculators and financial applications where that precision is really critical. Hexadecimal is used in quite a lot of places. We use it because it's a compact representation of binary data. We don't actually store any data on the computer in hexadecimal. Remember, it's stored in binary because we're using switches inside a computer. But when it's displayed or written on paper, then it can be shown as hexadecimal because it's more compact. We use it for memory addresses, we use it for web colors, MAC addresses, IPv6 addresses, so it's used in quite a lot of places, and mainly because it's a shorter version, you're less likely to make mistakes when you're writing and copying it, and it takes up less space on a screen or on a piece of paper. We need a way of representing negative numbers, and I mentioned this briefly before when we did our example of 10 minus 5. There are a couple of ways we can do it. We have ones complement method. In this, we flip all the bits in our number. So we take our original binary number, we take every 1 and make it a 0, and we take every 0 and make it a 1. and we say that's the negative representation of the number. 2's complement is very similar. You flip all the bits as before, but then you add 1 to the number as well. That gives you a 2's complement number. If you're using 1's complement to represent negative numbers, it's fine. You can, if you know that that's the way it's been done, you can tell what the negative number value is, but it does make arithmetic a little bit harder. You need special circuit to do that. 2's complement has an advantage that you can essentially just do column addition and they work. So for example, if we want to take a binary number like +5, that's represented with those leading zeros and 1, 0, 1. That's 4 plus 1 is 5. So the 2's complement of that number would be inverting every 0 to 1, and then every 1 to 0, and adding 1 at the end. You've got to remember always to add 1 at the end. You need to be consistent and remember to do it that way every time. Let's look at character representation. We need a way of converting characters and symbols to numbers because we need to store everything in binary. So there are various ways of doing this. One way was the ASCII, the original ASCII version. That was a 7-bit code used for letters, digits and symbols, but only allowed for 128 possible characters. 8 bits is a more common size for computers. It's a power of 2, whereas 7 is not. So extended ASCII uses 8 bits, and 256 characters are available in extended ASCII. It's still not enough for some languages, especially symbolic languages. So Unicode is used with up to 32 bits. So you can have an 8-bit Unicode or 16-bit or 32-bit Unicode, depending what you need. 8-bit Unicode is exactly the same as ASCII, so they're backwards compatible. Anything already created in ASCII can still be understood if you're using Unicode. But with Unicode you can have a lot more characters and symbols, so it supports all the major languages and emojis. Capital A in ASCII is 65, and that's the binary that would be stored on the computer for it. Smiley face emoji in Unicode, that one is represented there as Unicode. It's worth having a look at exactly what a character set is and how text is converted and saved on a computer. So a character set is all of the characters that a computer can understand. It can't understand anything that isn't in the character set it's using. So it's restricted to only the contents of the character set. Each character or symbol has a unique numeric representation, and that's stored as a binary number. When you're storing text, each character is converted to the binary value, and the values are stored in the same order as the characters occurred. So for example, the word cat can be stored in extended ASCII as a sequence of 3 8-bit values representing the letters C, A and T. C has a denary value of 67, there's the binary, A is 65 and T is 84. So all we have to do is, in that order, put the binary values. That must all be 8 bits, and they follow one after the other immediately in a string of binary digits. So it does look rather long. It certainly looks a lot longer than cat, but it's very easy to store this sort of amount of data on a computer, so it's not a problem, and it's a very effective way of storing character information on a computer.